Hi, I'm Ben-Yaakov. This presentation is entitled BLDC, Brushless DC Motor Made Simple for Power Electronics Engineers. Now, the objective of this presentation is really to present the very basic ideas behind a BLDC motor in a language that engineer or power engineers can understand, rather than the language that motor designers are using. We see here a basic configuration of a BLDC motor. We say here there are 3 coils. There is a magnet with 2 poles, and as we can see, the coils are energized such that they are actually pulling the magnet. So, for example, let's see here, here's a activation pulling the south side, and here's another activation pulling the north side. So we have a push and pull operation, because as we pull here, then we push here. For example, here we push this side. So by this we can move the rotor around. Now, the operation, of course, of this BLDC motor is based on the Lorentz force, which means that if you have a wire, there is a current through it, and a magnetic flux density or magnetic flux perpendicular to it, then there'll be a force. And this force is the force which is pushing the rotor. We have here a magnet, and we have here an electromagnet, which is pushing and pulling the magnets. Now, the force is proportional to the current, to the length of wire, and the angle between the two. Here it's theta, here it's actually alpha. Now, BLDC motor can come in many variations and can be driven by a number of ways. Here I'm showing a case of a single phase. Single phase means that we have only 2 wires. There's a single phase excitation, which is actually activating the coils. In this case, by the way, the magnets are outside, so the rotor is outside while the stator is actually inside. This will be suitable for, say, a wheel that you like to turn around. And in this case, we have a 3-phase motor. In this case, we have 3 phases, A, B, and C, and they are connected. Here you see that this one has A, this is B, and this is C, and as shown here, they're actually connected in a star connection. So there are many possibilities, and in variety of the coils, as well as the number of poles or magnets that you have in a brushless DC magnet or permanent magnet motor. Now, let's have a look a little bit deeper into the operation. We see here, in this case, again, the stator is outside, the rotor is inside, it's rotating in this direction. Here we're showing the winding. This is this way and this way. Actually, they are the same way, and here. And so by activating the coils, we can generate the electromagnetic force that is pushing and pulling the rotor, in this case, inside. So here is the rotor, here are the magnets. Again, we're talking here about a single phase operation. So let's have a look at this single phase operation. Here is the sinusoidal waveform, and in this case we are here at this point. This is the same current passing through all these windings, and while in this position we are pushing and pulling the magnet by the electromagnet. And then we move to this point, and by that time the magnet already rotated a little bit, and as you can see, we have here the poles are, or the direction of the magnetic flux is in the same direction, this is actually not a situation that is actually pulling or pushing or rotating the rotor. So in this case, nothing is really happens, and then it goes on to the other half cycle, which similar way, and again, and we are now of course activating the coils in opposite polarity. We talked about a single phase, but more popular and better is a three-phase motor. And in this case, we have three phases labeled here as U, W, and V. And here we have again, this is the rotor. We have 4 poles, or 2 pairs of poles. And then we have the coils around here. This is again the stator, and this is the rotor. So let's have a look what's happening in this case. Well, in this case, it's a 3-phase drive. So we have 3 waveforms, and I'm showing here the current through each of the coils. The red one, this is the blue one, and this is the black one. So we see here a sort of a starting point in which these coils, the W coils, are at 0, meaning that we are exactly at this point. So we have a excitation of the other 2 phases, which are a little bit off, and they are activating or pulling and pushing the rotor, both of them. And then we move one step further, and here we see the blue one. The blue one is this one, and here it is. This coil now is 0, and we have the other 2 coils now activated, these 2 coils now, and then it goes on and on. So what we see here is, due to the 3 phases, you might say that you have a rotating field here. It's moving here, and by this it is actually pushing the magnet. Now another advantage here, that we are avoiding the situation that we have a pole against a coil, and then the coil is activated. This is just wasting power, as in the case, let's say here, if there is, in this vicinity, we are just wasting power because the current is not contributing to the rotation of the rotor. So this is why a 3-phase system is much more popular, and it's more efficient and it's best. Another point is that in the case of a 2 pole, actually there is no preferred direction. Can go this way and this way, so you have to initiate the direction of the rotation. So this is one construction that I've shown, and there are many ways of building a motor. Here's another one. We see here it's a 1, 2, 3 magnets, or 3 pairs of poles, or 6 poles here, and then we have the windings. This is the winding, this and this, this and this, this and this. These are the electromagnets here. Now there is a difference between the mechanical rotation, that is, say, how long will it take the rotor to complete one cycle or one turn, and the electrical frequency, which is the basic frequency of, say, of this 3-phase waveform. And the relationship between the two is, this is the mechanical RPM, rounds per minute, divided by 60, it's per second. And then when you multiply it by P over 2, this is the number of poles, so this is the number of pairs of poles, will give you the electrical frequency. So this is the electrical frequency, and the rotation of the rotor is the mechanical frequency. Here is another construction. We have now many more poles here, many more magnets. Again, it's an outside construction. This is the rotor, this is the stator, here are the windings. So this is another way to go. And this is just a picture of a real motor, Samsung. We see the coils, we see the magnets here, the magnets which are being pulled and pushed by the coils. Now, let's talk about some electrical characteristic of the motor. One of them, a very basic one, is the back EMF. Now, what is the back EMF? If we look at one of the coils, we look at the windings here, say open circuit, while the rotor is rotating, what we see here, of course, is that the magnet is passing through this coil, and consequently, there is a voltage will develop here due to this relationship of the phi dt. The phi dt is changing due to the fact that the magnet is passing through the coil. And the phi dt is, of course, phi is A, the area, times magnetic flux density. So the voltage is a function of this rate of change. And the rate of change is a function of the rotation, the mechanical rotation of the rotor, because as the motor is turning, as the rotor is turning, it is passing through the coil, and the faster the rotation, the faster is the flux change. So therefore, we get a voltage with a function of the RPM. So the EMF, or the MMF as it's called sometimes, is a reflection of the fact that the magnetic flux is changing, or the magnetic field is changing around the coil, and it is proportional to the RPM of the rotor. And of course, this is RPM, and in hertz it will be RPM over 60. Now, what will be the shape of this EMF? Well, when the magnet is far away, there's nothing, but then as it approaches the coil, then you start building up a voltage as it is approaching. When it is against or just opposite the coil, there's basically no dphi dt or no dB dt, no change of magnetic flux. So therefore, you are actually here. And then as the magnet is leaving the coil, you get a negative voltage, because now the dB dt is becoming negative, it's becoming smaller. So this will be therefore the EMF typical of a coil while the magnet is passing through it. This is it, and of course in a three-phase system you get these three waveforms for the different phases. So while the rotor is rotating, it's generating this EMF, but the driving force is the input voltage. So for a given situation, neglecting now this impedance, which I'll talk about it in a second, Vin will be equal to E. So as you impose the voltage on the motor, it'll generate a back EMF eventually, which is equal to Vin, and which means that by Vin you're actually controlling the RPM of the motor. However, we have a difference here between Vin and E, because there is a inductance and resistance to the coil. Okay, so there is a voltage drop here between Vin and E, the electromagnetic force. Still, the driving force is Vin. As Vin builds up, there is a current here. This current is causing higher and higher rotation until you reach a steady state in which Vin plus the voltage drop here, or minus the drop here, is equal to the EMF. So we can say in general that the RPM of a motor, of a BLDC, is a function of Vin, and this is the direct way of controlling the RPM. If you like a higher speed, you have actually to increase the effective Vin that you are imposing on the motor. Now, as we generate an EMF, and we inject a current, there is a power. This is electrical power, which is of course converted to a mechanical power. Now the amount of electrical power will be dependent on the voltage and the current that we have at this particular coil or this particular phase. Now ideally you like it to be in phase with the voltage, that is the current to be in phase with the voltage, and by this you'll get the power, the optimum one. If it is not, if the current is say going over here or less here, then you do have a case of higher harmonics, or you might say circulating current, which is not contributing to the power, and therefore the efficiency will be lower due to the fact that the losses are a function of the RMS current being either the correct one or the in phase or not in phase, or the correct frequency or not. The losses are a function of RMS current. So you'd like the RMS current to be exactly the current that contributes to the power. Or you can look at it in another way. Power is the product of the voltage times current. Now these are not sinusoidal waveforms, so you can break them down by Fourier to the component at harmonics. Now we know that only products of the same harmonics will generate power, while product of different harmonics, that's the first and the third, generate zero current. So this is why you like the current to be as close a shape to the voltage, so that all the components will be similar to the voltage. So let's talk about now the mechanical power. Now mechanical power is the angular velocity, omega, times m, which is the torque. Now I'm labeling the torque as m, and this is the mechanical power. Now the angular velocity is related to the EMF, because we just said that EMF is the angular velocity, sometimes some constant. On the other hand, the torque is a function of the current. This is what we have just seen from the Lorentz force. This is generating the torque. So therefore, if I multiply the angular velocity times the torque, this times this, I'm getting this expression, which shows clearly the relationship between the mechanical power and the electrical power, and this is just for dimension or unit correction. So this is of course assuming no losses in the system. Now we can then summarize that we would like to have the current as close as possible to the shape of the voltage for the purpose of maximum torque and also lower losses or highest efficiency. Another important curve that characterizes motor in general and of course the BLDC is this relationship between torque and speed. Now this relationship is for a constant power, and typically you see that you have at low speed you can generate very high torque, and as the speed is going up you can generate less and less torque. Okay, so this is actually related to the very simple circuit or equivalent circuit that I've shown before. So to understand it, let's start from this point. Okay, suppose that I have V in, which I'm imposing, and there is no load, there is no torque. Therefore, there is no voltage drop here. So therefore, you get the speed of the motor will be related to V in, and this will be the maximum one possible, because V in is the voltage, the maximum voltage that we have. Now, we start loading the motor. Current is building up, and therefore there is a voltage drop on this impedance, and consequently the voltage that you have on the motor for a given input voltage, we're keeping it constant, the voltage that remains is lower, so therefore the speed goes down. Now we load it even farther, there's a larger drop, so E is smaller and the speed goes down, and so on and so forth. Now, when the motor is stalled, that is when it is sort of forced to not to rotate, then you have a very high current. These are low impedances, and the current will be very high. It will be here, the torque will be extremely high, and this would exceed a maximum level that you usually set up for the motor. So there is a line here which is actually the limit of the maximum current that you'd allow for the motor. So this is determined actually by the maximum current, which determines the maximum torque, and from then this point on it'll go down this way, maximum speed with no torque, and then as the torque goes up the speed will get lower and lower, and this of course for a constant input voltage. Now we can connect the coils in different ways. There is this star connection, and there is the delta connection, which is not used that frequently. One reason is that if the coils or the voltages which are generated here are not exactly the same, then you'll have a circulating current which is contributing to losses, and the efficiency will go down. So therefore the star connection is the most popular one. So a typical motor can be represented by the three phases, the impedances of the phases, and the EMF generated as the rotor is rotating and the magnets are passing past the coils. Now, in order to operate the motor, you need a driver, and typically this would be a three-phase bridge, three half bridges, and by turning these transistors on and off, you can generate the voltages here, which are imposed on the phases, and therefore controlling the RPM of the motor and of course the torque that will be available. Now there are many ways that you can turn on and off these switches. There are many modulation methods, and I'll just discuss two of them. One of them would be to sort of try optimize the system by turning on and off the switches just in time. That is, to turn the corresponding switches such that the current that will be built up will be in phase with the EMF, as we discussed this before. So you'd like, say, these two lines. Suppose this is the this line here is the line-to-line EMF. Then you'd like to turn, say, this transistor and this transistor on so that the current will pass or build up during this direction. It will not be a square wave because we have an impedance, but this is the best you can do, turning this and this when the voltage that you the effective back EMF here, these are two phases, and of course there is a 120 degree between them, but there is a total back EMF, and you like to turn these switches on when this we are passing through, the magnet is passing through the coils here, or effectively summing up these two. In this case, you are imposing the input bus on the motor, So therefore, if you'd like to increase the speed, you have to increase the voltage here. So the control, in fact, will be by increasing the bus voltage. The commutation is about the same, but you increase the bus voltage, therefore you impose a higher voltage and the speed will be higher. Another way would be not to turn these transistors on during all the time, but rather in a PWM fashion, so that you actually generate a average voltage which is lower depending on the duty cycle. This is now a fixed duty cycle throughout this period, and the average is of course proportional to the duty cycle. The higher the duty cycle, the higher will be the average. So in this case, the bus voltage is constant, it's high, it is the highest value, and you actually reduce it by modulating it with PWM and delivering an average voltage which is lower than Vin. So this would be one way to go. And here I'm showing some simulation that show what is really happening. So what we see here is the effective EMF. We see here, this is the gate control of the corresponding switches. And here is the current which is building up. As you can see, it is not square because we have the impedances, and we are also passing, this is between two phases, so we are passing through actually two phases, so this is actually explaining the break here. So this will be the current. Here we see the RPM, and this is the phase-to-phase voltage as you sum up the two back EMF of the two phases. Now another way is to generate a sinusoidal waveform between here, say two phases here, rather than a square wave. In this case, you'll have to change the duty cycle. Now the advantage of a sinusoidal waveform that it is smoother, and the motion of the rotor is with less ripple, and therefore this would be a preferable approach if you'd like to have a smooth operation of the rotor. So in this case, very similar to what we had before, except now that we have throughout this half cycle we have PWM, but this PWM now is with a variable duty cycle. Here is the maximum duty cycle, and here it is changing, here it's becoming lower. So the average voltage that you generate is a sinusoidal waveform, and by this, of course, with the three phases, you can generate a sinusoidal three-phase drive. So now we have the motor, we have an inverter, we understand that we can modulate the signal in different ways, drive it with different signals, and we may wish to measure the current for control and some other purposes. But what we need here, what we are lacking, is of course synchronization. How would we know to turn on the inverter in the right time? That is, we understand that the voltage that we drive or impose has to be synchronized with the EMF of the motor itself. So we have to have an indication what is the position of the rotor, so that we can turn on the signals or the drive in the right time. For that, we need some position sensor. And there are a number of sensors available. There are many types. I'm just showing two of them. One is very popular, and that will be the Hall effect sensor. So we have here now, this is the rotor. We can either use the magnets of the motor or different magnets, and these are Hall effect sensor which are sensitive to the magnetic field. So here is the element itself, a Hall effect element, and in this element will generate a voltage which is proportional to the flux density, magnetic flux density perpendicular to it. So when the magnets are passing here, there's a voltage generated. Unfortunately, it's a low voltage, it's temperature dependent. So there are some ICs that are actually taking care of both the amplification and temperature correction. Another possibility is to use an optical sensor. In this case, there are holes or slots sometimes, and then there are light sources passing through these, say, slots, and then there are sensors. And by looking at these signals and combining them, especially if you have slots of many types, you can tell what is the position of this disk, and this is sitting on the shaft of the rotor, so that you can tell what is the position of the rotor. I'd like to wrap up this presentation now with some specific subjects which are very important, but of course with this introductory presentation I cannot go into detail, so these will be very brief. So there are some buzzwords around the BLDC. There's the regeneration, sensorless control, and then which means that we don't use an external position sensor, field-oriented control, or FOC, and then there's the field weakening. And again, I'm going to present them in a very intuitive way, just to give a glimpse of what it is all about. Of course, the details are many, and just too much for a introductory presentation. So let me start with the regeneration. Now, when you have a BLDC motor, there are situations that you like to feed energy back from the motor, or the motor plus the load, back to the input, to the battery. This will be typical of a car. The car, you're braking the car, and during braking, you'd like to utilize the energy that you have in the motion of the car back into the battery as an electrical power. Now, there's two situations here that one has to recognize. One is when the voltage, the EMF, is higher than the bus voltage, or the peak of the EMF is higher than the bus voltage. This is generally will not be the case. The reason is that the EMF is a function in forward direction, is a function of V in, and so therefore it'll be usually lower than V in, except for situations, say there's a runaway car down the hill, then you might have situation that this EMF is higher than the input voltage. In this case, you really don't have to do anything, because if the voltage is higher, then you have here basically a three-phase rectifier. These are these diodes, which usually you will have, and then you actually rectify this signal back into the battery. This is a poor way to do it, and as I said, usually doesn't happen. More likely that you have a situation in which the EMF is lower than V in, you have a braking situation, and you like to get energy back into the inverter, or through the inverter to the battery. Now, the very basic equivalent circuit of this situation is the following. Suppose you have here EMF, let's say the motor is running, the rotor is rotating, so you have an AC voltage, and this AC voltage was generated by an AC voltage, let's say sinusoidal drive, generated by the inverter. Okay, so suppose it's a sinusoidal drive, and you feed in the signal. There is a current in the forward direction, and the motor is running. Now, suppose you'd like to brake. And let's assume that you reduce a little bit the amplitude of V in, okay, by changing, say, if it's a sinusoidal modulation, by changing the duty cycle. Consequently, the average voltage that is built up here is lower than the voltage here. So current will start flowing back into the inverter, okay? So this will happen if the effective voltage generated by the inverter is lower than, or a bit lower, because it's too low, then the current will be very heavy, very heavy current. So ideally it'll be a little bit lower, just allowing this current to pass from the EMF, from the back EMF, into the motor. This sounds very strange because as we've said before, this voltage is lower than the bus voltage. So how can it actually feed in energy back to the battery? Well, to understand here, I have a very simple sort of equivalent circuit, very general, you might say upscale equivalent circuit, that I think explains this situation. Now you can look at the inverter here as a buck circuit, because you have a bus and then you have PWM and you have an effective voltage which is lower. So basically the half bridge acts like a buck converter. So here is the buck converter. This is in the forward direction. You have T1, T2. T1 is when Q1 is on, and T2 is when Q2 is on. You like to turn it on to reduce losses, although it might be a diode here. Now the transfer ratio between V2 and V1 is like in any buck, the duty cycle, which is T1 over the total. This is the period now. Okay? But look at it from this side. This is a boost converter. And as this case, Q2 is, you might say, the switcher, while Q1 is like the diode. Okay? In the buck, this was the switcher, this was like the diode, and here we have a boost from here to here, and so this is the switcher and this is the diode. Okay? So first of all, we understand we can boost up the voltage. And the transfer ratio between V1 and V2 is now 1 over T off of the boost, okay? T off of the boost means this is when the boost is on, and this is when it is off. So this is T1 over T, and notice this is exactly like this. This is just the inverse, okay? So what this means is that for a given duty cycle, you can either look at the inverter as a buck which is feeding energy into the motor, and if the duty cycle is a little bit changed, not much, it will reverse the direction, and you will have actually energy coming from the motor into the V1. This is, in this case, the inductor of the motor itself. There's another resistor here which I'm not showing. This is not very effective because these inductors are small, so the RMS current in this situation could be very high, but still this allows regeneration, that is taking energy from the motor plus the load back into the battery. Let's move now to the sensorless control. As we have said, for proper operation, you have to synchronize the inverter or the operation of the inverter with the position of the rotor. We've talked about a Hall effect sensor, and then there is an optical sensor, but the sensorless control means that you don't use any external sensor. You can do it by looking at a phase, say this phase, if you look at this phase, then when it is not in operation, that is during that time, here this phase is on. I'm talking about this type of operation, which I have not mentioned. It's called a 6-step operation, 6-step modulation, or PWM. So if I look at this period when I'm not driving this phase, there is a zero crossing here of the EMF. That is, when I'm not driving it, I can see the voltage. I don't see it when I'm driving, because what I see is the drive voltage here. But if I'm not driving, I can see it here, and here it is. This is what I see when I look at one of the phases. This is when the phase is being driven, and this is during the off time. And you see that in this case we can locate the zero crossing, and by proper network and filtering, you can actually locate this time and this one time. So, and this will be for any of the phases. So by this, you can actually tell where the rotor is located, what's the position, and base the operation of an inverter on it. This will be therefore a sensorless control. Another issue is the field-oriented control. And what it means is a control which tries to maximize the operation by moving the phase of the current of the phase to be the same as the phase of the EMF. I am now approximating all the waveform by the first harmonic. So I'm saying that the back EMF is like a sinusoidal waveform. And what I like to do is to make sure that the current is, the first harmonic, is the same phase as the voltage. This will give me cosine phi of 1, the minimum reactive power, and the best operation in terms of losses, and also the for a given current, a maximum torque. Now, in order to get the current in phase with the voltage here, you need to feed in a voltage which is not in phase with this voltage. In fact, it's to be, you have to advance this V in, because you have a extra voltage drop, which primarily is reactive. So it's a 90-degree phase shift. So you have a voltage here plus a voltage here, or minus a voltage here, with generating this thing, or you have a, for a given current, you have to generate a voltage such that the current that will be built up will be in phase with this, and therefore you have to have a sort of advance of an angle. So you need here a delta phi to start the inverter production of this sinusoidal waveform that you feed to the motor a little bit in advance in order for the current to build up in phase. And this control is called field-oriented control. Now, the way to do it, there are many ways, and the classical one, which has been described in many, many papers and data sheets, is based on the state-space equation. So what you do, you write the state-space equation of the system, which is a 3x3 matrix, voltages and current, taking into account the inductances and the resistances. And then you use the Parr-Clark transformation to turn it into a 2x2 vector, 2x2 matrix. And then you solve it for the voltage that you need for the current to be in phase. And then you use a back or inverse Parr-Clark, should be a capital P, Parr-Clark transformation to get the actual angle in the three-phase domain. And this is how you calculate analytically, and this is usually done online by a microprocessor that is on board, which has all the information, and it can then advance the initiation of the inverter signal. Finally, I'd like to talk about another subject, which is field weakening. Again, this is an intuitive explanation. This is not how it is done, by no way. It's a rather complex subject, and so I didn't want just to write here equation, but rather to see the gist of the matter, what is behind it, okay? So what is the problem that we are trying to solve with field weakening? We have a motor, there is a V-in, and there is a maximum voltage that we have, okay? We understand that with this maximum voltage, you can get, let's go back here, with the maximum voltage you can get this maximum speed. That's it. That is V-in equal to E. Now suppose you'd like to, at a given moment, given situation in a car, for example, you like to accelerate and you like to get a voltage which is higher than this maximum. So here is the idea. Again, it's a notion. It's not the way exactly it is done. And the idea is the following. Suppose you have the motor running, okay? Suppose you have the motor running. And let's have a look at the first harmonics of the EMF. And this is this voltage here. Now, as the motor is running, suppose I impose on the motor for a short period of time the input voltage at this point. So I'm actually forcing the voltage at this point to be V-in. Now, as the motor is turning, this is just before, much before we got to the maximum. Okay, so there is a phase shift involved here. So once I do that, then this voltage is imposed while the motor is running, and the maximum could be higher. That is, the RPM will be higher. Now, to do this, there are a number of conditions. First of all, obviously, you can't do it if the current or the torque is very high. Because if the torque is high, then the voltage here is high, and you cannot impose this voltage on it. So therefore, this is possible only for low torque. Secondly, obviously, since you are off phase here, then you have a lot of reactive current, and therefore the losses are much larger. So the efficiency in this particular situation is much lower. However, as I've said, if comes to it that there is a need momentarily for a higher speed, this field weakening can be done. Again, we are not imposing a square wave, usually it's a sinusoidal waveform, but the idea behind it is pretty much what I'm showing here. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.